All right, let's get started. So welcome to this week's Coloquio, everyone. I'm very happy to introduce our speaker today. Her name is Asuka Kuwata, and she has recently joined our institute as a the GAPA postdoctoral fellowship, and she'll be working in general on energy astrophysics, but in particular on hopefully on gamma ray bursts and then afterglows. Asuka did her PhD quite recently, so she's fresh out of the graduate school in March. She finished her doctorate in physics from Tohoku University. I don't exactly know where it is, but I think she will point out. I think we all know major cities like Tokyo and other places in Japan. And I met Asuka a couple of years back in Italy. I guess she was presenting a poster in a conference on her PhD work. And today we will hear more on what she did in her dissertation, which is on gamma ray bursts, afterglows, and polarization. So thank you all.
Yeah, thank you for nice introduction. Yeah, nice to meet you. Yeah, my name is Asuka Kuwata. Yeah, so I am my PhD in Tohoku University in Japan, which is located in the northeastern part of Japan. Yeah, then I did for 6 months a postdoc at same university, and then after that I came here to make this. And my interest is on research. It's the hierarchy astrophysics and gamma ray bursts and polarization. And my hobby, hiking and anime and reading books. Yeah, this is a picture of the theoretical astrophysics groups in Tohoku University. Yeah. So yeah, this is me, and this picture is the my PhD supervisor Kenji. Yeah, I hope I can enjoy the hike and also Moralia and other parts of the school. So let's move on to the research part. Yeah, today I will talk about the theoretical modeling of gamma ray burst afterglow. So let's start about what is gamma ray burst and afterglows. Gamma ray bursts are the most brightest gamma ray transients in the universe, and its energy, total energy, is about the 10 to the 49 to the 10 to the 55 ergs. And its typical duration ranges from several 0.01 seconds to the several hundred seconds. So after this gamma ray burst happens, the long rate and broadband from radio to gamma ray emission is usually observed, and this emission is called afterglow. Yeah, so this is the standard picture of the gamma ray bursts and the afterglows. So the projector of the gamma ray bursts are the black hole and accretion disks, which created by the binary neutron star merger and collapse of massive stars. So this central black hole and accretion disk driven relativistic jets, and these jets dissipate its energy as a gamma ray burst. So this gamma ray is observed as the gamma ray bursts. So after gamma ray burst is emitted, this relativistic jet goes into the interstellar medium and then sweeps up the interstellar medium and create shock waves. So at these shock waves, the electrons are non-summary accelerated and emit synchrotron emission. So this emission is observed at the afterglow. Yeah, so I will mainly focus on this afterglow phase in today's talk. Yeah. So this is the schematic illustration of the afterglow light curves especially on X-ray bands. So at the initial afterglow phases, so the shock is expanded and so because of the afterglow shock waves is the go in the relativistic speed. So due to the Lorentz beaming effect, we can only observe the region within the 1 over angle of 1 over gamma. Yeah, due to the beaming effect. So we only see this white circle region. But this 1 over gamma region is still smaller than the angular size of the shock itself. In this case, the flux decay rate is like this. And after this shock expands, as the shock expands to the more further away, so this shock wave accelerates due to the conservation of the energy of the afterglow energy. So this shock waves accelerate at R minus 3 over 2. Yeah. Then, as the shock accelerates, this 1 over gamma region expands as this right figure. Yeah. And at that time, so when this 1 over gamma beaming region exceeds the region of the angular size of the shock itself, so now we only see this gray shaded line. So in that phase, the flux decay rate will increase, and there is the break in the right curves. So this time it's called jet break time. Yeah.
What is the P? What determines the parameter P?
T, jet break rate.
The P parameter, T to the minus P. What is P?
Yeah, sorry, I forgot. So P is the electron power law. Yeah, so electron energy distribution. So electron energy distribution can be like the electron length factor to the power of the minus P. Yeah, so this is determined by the power law distribution of the non-thermal electrons. Yeah. Yeah, thank you for question. Yeah. So then next, let's move to the energy conversion in the afterglow shock waves. So the original energy source of the afterglow emission is the upstream kinetic energy of the gas stream motion. Yeah. And at the afterglow shock wave, this upstream kinetic energy is dissipated into the thermal energy of the downstream. Downstream is behind the shock front. And some part of thermal energy is converted to the magnetic field and non-thermal electron energy. And this is the relativistic electron, and this relativistic electron and lose their energy by the synchrotron emission, and this magnetic field non-thermal electrons account for the observed synchrotron flux. So, however, so in this energy conversion process, there are two main questions. Two questions. So first one is the magnetic field amplification process. So in this afterglow shock waves, so there is a magnetic field, but the value of the magnetic field is 100 times stronger than, more than 100 times stronger than shock contrast industrial field. So this at the downstream magnetic field must be amplified. Yeah, but we don't know how to amplify such a strong field. So, and second question is the particle acceleration process. So we know the particle is accelerated by the diffusive shock acceleration, but how to determine the energy fraction of the non-sound particle is still unknown. So, and these two questions is very related to the downstream magnetic field structure. So, to clarify the entire energy conversion process in this Afterglow relativistic shock wave, it is important to understand magnetic field structure in the downstream region. Yeah, so let's continue to talk about the basic knowledge of the afterglow shocks. So I said the afterglow is the relativistic, and also the afterglow shock waves are the collisionless shocks. So in the collision means the Coulomb collision, and in the on normal collisional shock waves. So in these shock waves, Coulomb mean-free path of Coulomb scattering is much smaller than the scale of the length scale of the astronomical objects. So in this case, the upstream kinetic energy can be dissipated by the Coulomb collisions due to these relations. So these collisional shock waves can be seen in the shocks from supernova explosions or molecular cloud collisions. On the other hand, the afterglow shocks are collisionless shocks. So this means the mean-free path of Coulomb collision is much larger than the length scale of the astronomical phenomenon. Yeah. So in this case, these shocks can't dissipate energy by the Coulomb collision. Yeah. So on the other hand, this collisionless shock dissipates the upstream and upstream kinetic energy by the electromagnetic wave and particle interaction. So these kind of shocks can be seen in the gamma ray burst or pulsar nebula and the active galactic nucleus. Yeah, almost rarely high energy phenomenon. Yeah. So there's also the important physical property of afterglow shocks is these shocks have the scale of the emission region. Yeah. So afterglows are emission from relativistically and adiabatically expanding spherical shock waves. And in this case, we can consider the downstream density as the self-similar profile. So which is called Branford-Markey solution. And according to the Branford-Markey solution, downstream or other physical physical value in the downstream shocks decreases on the some typical spatial scale. So this spatial scale can be written as the delta R dash, and this is roughly R over 16 gamma. Yeah. Yeah. So there is a characteristic scale in the downstream region. Okay, so then from now on, So in the previous slide, I said that so understanding the magnetic field structure is crucial. So then from now, let's move to the turbulent magnetic field model in downstream of the afterglow shocks. So far, there are mainly two magnetic field models have been considered. And first one is the microscopic scale magnetic field. This magnetic field is amplified by the plasma kinetic instability. So, and the field scale is about the proton plasma spin depth scale. So this is a scale at which electromagnetic waves and particles can interact with this scale. So this microscopic scale field is needed to generate collisionless shocks. And so many researchers have been involved to do particle insertion simulations to reproduce this microscopic scale magnetic field model. So this is one of the results. And the right side is the upstream, and this is a density profile. And so at the shock waves, the density is jumped according to the shock jump condition. And so there is a shock in this here. And also the magnetic field is amplified at the shock front. Very increased at the shock front. However, as you can see, so this amplified magnetic field dumps quickly at the downstream region. And this magnetic field dumping scale is at least 5 orders magnitude smaller than the scale of the emission, the sequence of the emission region. So, because of these quickly dumps, this microscopic scale field may not account for the observed synchrotron flux. Then another magnetic field model is also considered, and this is to generate such a, so this turbulence has the more larger scale than the microscopic scale field model. So to generate such a large scale magnetic field, we consider the magnet hydrodynamic instability and lithium-ion mesh instability. So the concept of the this lithium-ion mesh instability is like this picture. So at first, in the front of the shock, there is a density fluctuation and uniform magnetic field in the industrial medium. And so as this shock waves, after the passing the density fluctuations, this density fluctuation non-linearly evolved and leads to the turbulence in the downstream region. And due to this turbulence, the magnetic field also magnetic field amplified things. So this is the amplification rough explanation by the image instability.
May I ask the question?
Yeah.
What regime of plasma data are you in? The plasma data parameter.
Plasma data.
What regime are you in? Is it low or high?
Not so in the afterglow shock waves, plasma beta is not so high. So
So it's already magnetically dominated. The pressure
sorry. Plasma beta is high. So
is high. So it's,
yeah. So not magnet.
it's
Stronger magnetized.
the thermal pressure is much higher than the magnetic pressure.
Thermal pressure.
Well, so
Yeah.
plasma beta goes as the inverse of magnetization. So the magnetization in the upstream medium is of order 10 to the minus 9. So it's
very low.
plasma beta is high.
Okay.
Yes,
Okay.
magnetic field is rather small, which gets amplified downstream.
And even when you amplify the magnetic field by factors of 1,000, it's still
So the magnetization is of order 10 to the minus 3-ish. So it's, yeah.
Thank you.
Yeah, thank you. So by considering this MHD instability, so large scale, we can consider the large scale magnetic field as the amplified magnetic field in the downstream region. So in this magnetic field model, the coherence ranks of the scale of the magnetic field is the order of the thickness of the emission region. Right, that, yeah. So, in this large-scale magnetic field model, this field can account for the observed synchrotron flux. And so, yeah, I don't explain about it, but so if there is only microscopic scale turbulence, so it is difficult to accelerate particles higher than the 10 to the 17 electron volt. But if there's a large scale turbulence, it can be accelerate more high energy particles than 10 to the 17 electron volts. So, as I explained, there are two turbulence magnetic field models have been proposed. However, especially in the microscopic scale magnetic field, so due to the limited simulation resources, we can't resolve the whole region of the thickness of the shock wave, thickness of the emission region. Thus, we cannot conclude which turbulence dominates only from the current numerical simulations and right curve data. Then, it is crucial to clarify the magnetic field structure from polarization. And then, also the application of the polarimetric studies is the properties of circumstance we can know the properties, we can investigate the properties of circumstellar medium and the high energy cosmic ray acceleration process and prompt emission efficiency. Then, so what is the typical value of the afterglow polarization? So this is the time and this is the polarization degree in the afterglow. So at the early time afterglow, so in which phase reverse shock emission is dominated. So due to the, so in this phase, the polarization degree tend to be higher from 10% to the 30%. On the other hand, in the late time afterglow phases, so at which forward shock emission is dominated. So afterglow polarization degree is low, and it ranges from 1% to 5% or 3%. Yeah. So in this talk, I focus on the late afterglow, which is forward shock dominated phase. Yeah. So the typical value is 3%. Yeah. Then how about the theoretical model of polarization? So in the microscopic scale magnetic field model, there are, people have, there are a lot of works in this microscopic scale field model of polarization. Yeah. And the time dependence and frequency dependence are well understood in this model. However, on the other hand, in the large-scale magnetic field model, there are only rough estimate of the polarization degree. So, it says that polarization degree is the 70% over root n parts, which means 70% is the polarization degree in the case of uniform magnetic field in this synchrotron emission. And the large n patch means the number of patches within the magnetic field is uniform. Yeah. However, this estimate is for the isotropic magnetic field. So we don't know dependence on time, frequency, field, anisotropy, and viewing angle in this model. So I constructed the theoretical model in the large scale magnetic field. So this is the end of introduction, and I will move on to the microscopic scale model and observation. Yeah. First, I will show the concept of photon equal arrival time surface, which is important to understand the polarization. So let's consider the emission from the shock at the sometime t0. So in this case, emission from the line side, this is observer, and this emission from the line side arrives earlier than that from the slightly deviated direction, this orange line, because of the curvature of the shock itself. So, but we would like to consider the point that which photon arrives at the equal time for the observer. So to consider this, we should consider the emission from the T0 plus delta T at around the line of sight. So in this case, emission from the line of sight at T0 plus delta T, and from the emission from the deviated direction at T0, this emission arrives simultaneously to the observer. Yeah. By considering this effect at each point of the shock waves, we can define the imaginary surface inside which all photons reach the observer simultaneously, and like this egg-like shape. And this, we call it equal arrival time surface, or EATS. Then, so the important point of this EATS, equal arrival time surface, is the emission time at the slightly deviated region. So this is the angle of 1 gamma. This emission time here is earlier than the emission time at near the line of sight. So let's consider the surface brightness profile in the afterglow. So yeah, so when considering light curves of the optical and radio band, so in the optical wave band, the afterglow decay rate is more quickly than the radio band. So as the shock expanded, optical shows more steep decay. And due to this effect, so in the optical band, we can see that in optical, the emission is bright at the over gamma region. So this is the image of the plane of sky from the ground. So on the other hand, in the radio band, the right curve shows shallow decay in the optical. So this image on the plane of sky looks like more dimmer and more flattened than the optical image. So the frequency dependence of these surface brightness leads to that of polarization. Yeah, so next, this is a parametric property in microscopic scale turbulence. So now we consider, in this microscopic scale field model, the local polarization is determined by the average Stokes parameters with respect to different distributions. And so we now consider the slightly finite observer viewing angle. And so in the microscopic scale field model, so there are two factors to create net finite polarization degree. First one is the local field anisotropy, which creates the local polarization degree, And second one is the asymmetry of the observable region due to the jet brake. So these two factors make a net finite polarization degree like this figure. And also surface brightness profile and local polarization degree distribution makes optical polarization degree much higher than the radio polarization degree. So let's see how the polarization degree evolves in this model. So this is the time evolution of the polarization degree. And at first, so this is the image. And so we only see the region within the 1 over gamma. In this case, so the local polarization cancels out. So we don't observe any polarization signal. So, but as time goes by and the shock decelerates, this 1 over gamma region bigger, and the observable region breaks the symmetry, and there must be the polarization signal. As further goes time, the polarization angle shifted by 90 degrees. So at that time, polarization angle is 90 degrees, and at that time, net polarization angle is 0 degree. So the polarization degree peaks around jet breakdown, and the optical polarization degree here is the always higher than the radio polarization degree here. And polarization angle shows 90-degree flux between these two peaks. So this is the property of microscopic scale field. Then let's compare to the model with the observation. So there are several about 30 to the 40 optical one event which is consistent with microscopic scale field model. So I mean that this event shows 90-degree flip of optical polarization angle around the jet vector here. Yeah. However, there are also events which is consistent with the model. So for example, this event doesn't show 90-degree flips around the jet break time. Yeah. And this event also inconsistent to the model in points that there is no polarization degree peak at the jet break time is here, but no polarization degree peak. So from these events, so microscopic scale field model is inconsistent with at least some observations. Yeah. So yeah, then finally I will move on to the main part, my PhD works, so large scale magnetic field model of polarization. Yeah. So in the large scale magnetic field model, so in the previous study, there is only order estimate of polarization degree in this field. So this is due to the large uncertainty in the spatial distribution of turbulent magnetic field. And there is also the parameter size in various ranges is difficult for MHD simulations. So in this part, so we focus on the large scale field model in supernova remnant shock waves. So this is the non-relativistic shock waves. But so there is a works which calculate polarization in this supernova remnants in the large scale field model. So based on these works, we also consider the relativistic effect of afterglow shocks, and we take into account some approximation of magnetic field radial distribution. And by combining them, we finally create the semi-analytical model of large-scale magnetic field model. Yeah. So in this model, polarization, we calculate polarization by integrating over the equal variable time surface in the 3D turbulent magnetic field. Yeah, so this is it. For the magnetic field model, yeah, we just using summation of uniform field and random field. Today I will show you only the result of no uniform magnetic field case. So, and one of the big assumptions in our model is that the length scale of magnetic field in commutating plane is the thickness of the emission region, and we introduce FB as the parameter. Yeah. So this is the calculation result. So let's see the dependence of field anisotropy on the local polarization angle. So there are image of the sky of plane of sky, and the left feature the anisotropy field local polarization angle distribution. And right is the anisotropic field case. In the isotropic field case, so this is the observer viewing point, and this is the depth axis point. Yeah. So orange is the radio bright emission region, and the optical purple is the optical bright region. So in the isotropic field case, local polarization angle direct randomly in the all region. Yeah. On the other hand, in the anisotropic field case, so local polarization angle or radially oriented at the optical bright region. And on the other hand, in the radio bright region or inner region, yeah, local polarization angle also becomes random. Yeah. So this is the property of the local polarization angle distribution. And so we can see the polarization degree, time variation polarization degree from, yeah, we can consider the polarization degree time variation from these profiles. Yeah, so let's see the time variation of the polarization degree in the isotropic field case. So left figure is the time variation polarization degree in the when which calculated in the 1,000 realization. So, and the right figure is the average polarization degree over the 100 different turbulent realization. Yeah. So, in the isotropic field case, polarization degree and polarization angles vary randomly and continuously, and optical polarization degree and radio polarization degree is same level on average. However, at some times, optical polarization degree is smaller, can be smaller than the radio one. So, on the other hand, in the anisotropic field case, so this is also the 100 realization calculation. This is the 100 average polarization degree. So in this case, optical polarization degree peaks at around jet break time, and polarization angle also shows 90-degree flip. So this is the similar behavior to the microscopic scale field model. But in the radio band, polarization degree is random, and polarization angle shows a bigger flip than the optical one. Yeah. So from this result, we can interpret the rate time afterglows with our model. So there is one event which shows 90-degree flip of optical polarization angle. So with the large scale field model, if the field is highly anisotropic and highly anisotropic, so these polarization angle flips can be maybe reproduced. And so there is also event which shows no polarization angle flips. So this continuously changed polarization angle can be explained by the isotropic field case. And also, this event doesn't show polarization degree peak around jet break time. And this also can be explained by the nearly isotropic field case. So, the large scale field model could explain all the observational data to date. Yeah, so here's a summary of my talk. So during my PhD, we construct a large scale field model of force shock afterglow polarization. So study for microscopic scale field model, the time variation polarization degree polarization angle in uniform or symmetric jet models is inconsistent with some parametric observations. On the other hand, in the large-scale field model, it likely shows 90-degree eclipse if magnetic field is highly anisotropic and shows consistent polarization degree with observations in nearly isotropic. Yeah, so this model could account for all parametric data from forward shocks. Yeah, by now. Yeah. So to constrain the turbulence models, we will need the time-resolved spark optical and radio parametric observation around jet break time. So if we find optical polarization degree is smaller than the radio polarization degree, random variations of polarization degree, polarization angles, so the large-scale model will be most likely. And now, yeah, I'm doing magnetic hydrodynamic simulation to verify the assumption of our turbulent model and to investigate scale of anisotropy of magnetic field. Yeah, okay. Thank you for.
Okay, perfect timing. Lots of time for questions.
So do you know what the physical process is that would give rise to an isotropic field in one source and an isotropic field in another? What would be the difference?
Yeah, so I said that in the
You'll have to share your screen.
in the case of MHD instabilities, so at least in the linear phase, this turbulent this density fluctuation elongated in the direction of the shock normal direction. Yeah. And however, when it goes to the turbulence phase, maybe turbulence is more isotropic. So
And how far downstream you are?
So it depends on how the instability works in this shock phase. So this is what I would like to investigate in the MHD simulations as the next step.
Would your MHD simulations follow the amplification of the magnetic field as well? Or is that something you're opposing? Like, are you starting in the upstream before the shock? And following all of the turbulence and the amplification? So these must be very large resolution.
Exactly.
So where are you running? Are you running on the or do you have a supercomputer?
We plan to run it here if we can do it in one of the machines. But I think at the moment you're doing some calculations in Japan. You have a cluster in Japan. And she's using Athena++ to do this. But briefly to add to what Asuka mentioned about your question, the microscopic model that she mentioned earlier, which generates these small-scale magnetic fields, those are highly anisotropic, meaning all the magnetic field lies in a plane perpendicular to the shock normal. Okay. So those would be the situations, as you asked, where you can get a highly anisotropic field. Then you need something else to mix the fluid downstream and stretch it out to make it more isotropic. So the expectation is that some kind of instabilities, what Asuka mentioned, the Rickmeyer-Meshkov instability, which can be seeded from the upstream region, would be able to generate more isotropy in the magnetic field. We don't know to what extent you can get that, and that's what she's going to be looking at.
synchrotron.
Yes, please.
I have one question. It's more related to the observation part. So, regarding the optical polarizations, so how many days after the GRB event you were doing the optical polarization observations? Or immediately after that event is triggered, you were doing the observations?
So how many observations?
So when do you make the measurement of polarization from afterglow, after the GRB? How many days or how many hours or time? What time?
Yeah, so there are both are observation from the
Can you make it full screen?
yeah.
Oh, okay. You have to share the full screen anyways.
And
Yeah.
the 100 seconds in the early phase. And at the time phase is about 1 day to the 10 day. So
Okay, here's my question. This is an interesting figure. You see a drastic difference between the late time polarization, which you mentioned is few percent,
yeah.
and then you have very high polarization earlier on. What's the difference, and why is there's such a huge difference?
Yeah, so in the early phase, the emission from the reverse shock is dominated, and the reverse shock is the shocked jet ejector. Yeah, shocked ejector from shocked ejector, and this ejector may have the more strong and coherent, more like uniform magnetic field. Yeah, so it may account for these high polarization. Yeah.
Okay, so the emission is coming from two different regions. One is the reverse shock, which is the shocked ejector,
Yeah.
and one is the forward shock, which is the shocked ISM.
Yeah.
So there are two different regions, and they have different magnetic fields.
Yeah.
Okay.
Okay. Yeah.
Hey, sorry to interrupt. There is a question on Zoom.
Yes, please.
Alice, go ahead.
Thank you, Sundar. Hi, I'm Alice. Yeah, probably I missed this information during the talk. I have two questions. So, what's the scale of your experiment, and also regarding the instabilities? Which kind of instabilities are you talking about? They are Kelvin-Helmholtz instability, advection instabilities?
Yeah, so your first question is what is the scale of the afterglow
Simulation.
Simulation of the MHD instability, right? Yeah, so the scale is about the so the plasma skin depth is about the 10 to the 7 centimeter, and the thickness of the emission region is about 10 times larger. So the scale is about 10 to the 17 centimeter, well, sub-parsec scale.
Sub-parsec scale?
Yeah.
Okay.
So this is the right time afterglow shock waves.
So it's very unlikely to have advection instabilities, maybe in at that scale, right?
Advection instability. Sorry, I don't know much about the advection.
What's an advection instability?
Yeah, so in this simulation, we saw the raised microscope instability, which is induced by the upstream density fluctuation and the shock waves. Yeah.
Okay. Okay, thank you.
Yeah, you're welcome.
Okay, more questions. Do we know the radio polarization? You mentioned there's a test of your model, which is if it displays a different polarization angle in optical and radio.
Yeah.
Do we have an idea of what do you measure in radio and what the polarization angle is? Do we have any observations?
Yeah, so regarding, yes, thank you. So regarding the radio polarization, I only, yeah. Yeah, so there are only three or four events in the radio band. Yeah, and so at that time, yeah, at that time, so for example,
Okay.
so do you want to ask what's the
0.2, is that 0.2%?
yeah, it is 0.2%.
Okay.
And yeah, the other event shows 1%. Yeah, but it is lower than the optical polarization difference.
Generally, it's much lower, right?
Yeah,
Okay.
yeah. So, but we only have 3 events which of radio polarization observation. Yeah, so we have to increase the number of events.
Okay.
And see the statistical property of the radio polarization.
Okay, any further questions? Anything else on Zoom, Sundar?
No, we don't have any more.
Okay, well, let's thank our speaker in that case.